tasked to find the volume bounded by this graph. Y is equal to square root of x, y is equal to 2, and the y-axis. Now, that graph would look a little something like this. So how do you think we're going to solve it? Well, we will be using the cylindrical method. And to start with the cylindrical method, we're going to have to visualize this graph a little different. Something like this. See this? Now, assume that these, from this y-axis bound, you have this infinite amount of cylindrical shells, like this. This green and gray thing here. We will be finding the volume of each of those cylindrical shells, and we're going to do that by using integration. So to start, we're going to first find its components. The radius of that shell would be this here, which is essentially this function, and the 0 in this y-axis. So the radius is that function, and the height would be this slimmer of the shell. That's going to be the height, and of course there's going to be like a lot of those, since we're going to be using an infinite amount of cylindrical shells for that bound. So we assume that those are just dy, and using those we get this formula. V is equal to pi times the limit bounded by the graph, which is C and D, that the integral of the radius squared times dy. And you can tell that this formula looks pretty familiar, since this is actually derived from the cylinder volume formula, which is pi r squared h. So you can see that resemblance right here. Now, getting to the solving part, let's say you are to solve that graph, the volume of that graph. And oh, by the way, I forgot to add, but this, you will be solving that volume revolving around the y-axis. You could see that the cylinders there were wrapping around the y-axis. And because of that, we will be solving the function in terms of y. And that's why this is the formula we got, pi integral of r y squared dy. So we'll be solving in terms of y. And because of that, we will be getting this. Pi times integral of y squared, and we got y squared because of this. We essentially square to remove the square root. Square this to remove the square root of x, and because you will be getting y squared. So there, you get y squared in the function, and that raised to the power of 2, with the limits of 0 to 2. And we saw from the graph that the y-axis had a bound from 0 to 2, and 2, you see that from the value here. So yeah, you get 0 to 2. Again, we're just going to be solving this. So we're going to be getting y raised to the 4th power, and we're going to be finding the integral of y raised to the 4th power, which is just going to be 1/5 times y raised to the 5th power. And we will be inputting the limits in that. So you get 2 raised to the 5 times 1/5 minus 0 raised to the 5th. So this is just automatically 0. So 2 raised to the 5th power is 32. And our final answer would be 32 pi over 5. So that's going to be the volume of this bound revolving around the y-axis. Let's try something different. Say you are given this bound. Y is equal to 5 times the square root of x is equal to 1, x is equal to 3, and the x-axis. And we will be solving this time revolving around the x-axis. Now we're going to be revolving around the x-axis. And what that graph is going to look like is something like this. Sorry, the image is cropped, But essentially, the limits of this x value and this x value is just 1 and 3. So sorry, you couldn't see it, but the limits of this is just 1 and 3. Now, since we will be revolving around the x-axis, sorry, I didn't put this in, so I'll just type it. So this we'll be revolving around the x-axis. Because of that, we will be solving in terms of x. So you can see that our formula that we will be using is just the same, except we just altered the limits to be from c to d into now from a to b, which is the x limits, and the function to be in terms of x. So you get this, and the function is as is, since we're going to be using in terms of x. We will be using 5 times the square root of x as the function, and the limits to be 1 and 3. Okay, so essentially we're just going to be solving this. So square these two, you get 25 times 5, and we bring out 5. We bring out 25 rather. Sorry. And we input the limits into the x here. So this is what it's going to look like. 1/2 times 3 squared minus 1/2 1 squared, and this becomes just 1/2 because it's multiplied by 1. This becomes 3 raised to 2, which is 9, so 9 over 2, and you will be getting 8 over 2 here. 25 times 8 is 200 pi. 200 pi. Yeah, 25 pi times 8 is equal to 200 pi over 2, and what you'll get is 100 pi. Actually, I didn't instantly solve it. What you could do is just divide 8 by 2, so you'll get 4, and 25 times 4 is just 100 pi. Either way, you get the same answer. So the volume of this revolving around the x-axis is 100 pi. Now we're going to be trying something different. Let's say you were given this bound, and you were supposed to find the volume of it. Y is equal to x squared, y is equal to x plus 2, and the y-axis. Now, you could notice that there are two functions here. One exponential function and one linear function that looks something like this. I actually already made the graph. The graph of this. This is what the graph looks like. This thing. And now, what we're going to be doing is no longer the cylindrical method, but what we're going to be using is no longer the disk method, but the washer method. And you could think that the washer method is different from the disk, but it's actually not. It's very similar. See this function here? It's very similar to disk method formula. This method formula, but you can see that there is two functions now. And the way this works is a washer is just a cylindrical shell, a cylindrical disc, but with a hole inside. See this? There's a hole inside. So the way that translates to the graph is essentially we will be only finding the volume of the bound. You can see the bound here. So there is this one huge cylinder that wraps around here. Cylindrical disc. Sorry. Yeah, cylindrical disc. But you can see that there's a hole here. There's an area where there is no bound. So what we're going to be doing is subtracting that area without a bound to this whole area with this whole volume with the bound. So that's why we will be subtracting this Rx, this big Rx is the outer radius. So that's the uppermost. That's using the uppermost function minus the innermost radius, and that's this little area without a bound. That's the inner radius. So essentially, we're just finding the volume using the cylindrical disc, but it just has a hole, and we just have to subtract that. This, by the way, is revolving around the x-axis. Sorry, I didn't put it. But we will be solving this revolving around the x-axis. That's why we're solving it in terms of x. So finding all this revolving around the x-axis. Okay. So now now that we have our formula, what we'll just be doing is substituting. So 0 to 2, you could see that the bounds there was 0 to 2. It's not stated in the given that there's 0 to 2. So what you would like to do to find the bounds of that of the x-axis, which is 0 to 2, is essentially just equating these two functions, and you will eventually get into the answer of 0 to 2. So that times the outermost radius, which you could notice was the line, so it's x plus 2, minus the innermost radius, which you could notice was the exponential function, so it's x squared. And we're just going to be squaring these two functions. The square of x plus 2 is x squared plus 4x plus 4, minus the square root, the square of x squared is just x4. And we will be finding the integral of each of these. So it's going to be just, the integral of x squared is x cubed over 3. The integral of 4x is 4x squared over 2, or just 2x squared. The integral of 4 is 4x, and the integral of x raised to 4 is just 1/5 times x raised to 5. So what we're going to be doing is substituting the limits into those y's. Again, we just put 0 on the other part, since all of this is essentially just 0. So we'll be getting is this. 2 times 2 times 2 is 8. So 8, 3 plus 2 squared is 4 times 2, which is 8. Then 4, 2 is, you will get 8 if you multiply those, and you will get 32 over 5 if you square, if you raise 2 to the 5th power. So 32, 5, so minus 32 over 5. And if you do all of this together, you will be getting the final answer of 184 over 15 pi. And that is the volume of this bound that revolves around the x-axis. Now, say, what if this time this function revolves around the y-axis? Y-axis. There. So the formula will not change, but we will alter it so that we are now solving it in terms of y. So this is a to, the limit of a to b is changed to c to d, and that limit is just 0 and 0 to 4. Again, it's not really explicitly stated that the limits of the y-axis is 0 to 4, but you can essentially find that by just equating these two functions. Then, so there, 0 to 4, 0 to 4. Now, we will be finding the outermost radius in terms of y. So the outermost radius here is, since we're doing it in the y-axis, in respect to the y-axis, which is the outermost function, that would be x squared, or square root of y in terms of y. So the outermost radius is going to be square root of y squared, minus the innermost radius, which is now this, the linear function, which is y is equal to x plus 2, or to get this in terms of y, we just subtract 2 to both sides. So you'll be getting y minus 2 squared. And again, we're just going to be squaring those two functions. Square root of y is just y, because it cancels out, and the square of y minus 2 is y squared plus 4y minus 4. We're just going to be finding again the integrals of each of these. But before we do that, we're going to be, since there's a like term here, we're going to be adding y with 4y, so that becomes 5y minus y squared minus 4. And then we will be finding the integral of each now. So 5y is just 5 halves y squared. The integral of y squared is just y cubed over 3, or 1/3 times y cubed. And the integral of 4 is just 4y. So we will be substituting that. The 4, 0. Again, we assume that, we don't really assume, but we substitute this to be zeros, and that just instantly equates to 0. 4 is substituted among the y. So 4 raised to 2 is 16 times 5 is 80 over 2, which is 40 here. 4 raised to the 3rd power is 64, so 64 over 3. And 4 times 4 is just 16. And if you solve all of that, you will be getting the final answer of 8/3 pi. And that is it for the washer method. Now, finally, let's say you are tasked to find the volume of this bound. Y is equal to x cubed, x is equal to 2, y is equal to 0, and the y-axis. So this time we will be using the cylindrical shell method. Again, the graph of this looks something like this. But to visualize it for the cylindrical shell method, we will be adding this cylindrical shell. Now the way this works is that there's going to be a tiny slip here, this blue rectangle, you see this? Blue rectangle. What we will be doing is putting that a lot in our graphs, and this is going to be our serve as our guide for the cylindrical shell. This rectangle slip is always parallel to the axis of revolution. So, sorry, I did not say this before, again, but we will be solving this in revolving around the y-axis. Sorry, these two are different, okay? Y-axis means it's bounded by the y-axis, but this means it's revolving around the y-axis, the other y-axis, sorry. I didn't clarify that. So the way this works is we are essentially finding the volume of a cylindrical shell, and the cylindrical shell is essentially this, a cylinder that's hollow, pretty hollow. So what we will be doing is finding the volume of that shell. And for the volume of that shell, this singular shell alone, the volume of it is 2 pi r h w. I didn't write the exact derivation for this, but essentially this is gotten from subtracting the volume of the outer cylindrical shell with the inner cylindrical shell. So that's going to be pi r squared h, pi outer radius squared h minus pi inner radius squared h. And if you factor that, and you solve it so that these r's, these r's are averaged, so you get the average of the radii, average of the radii, and essentially you get this little formula. So 2 pi r h w. And to translate that into integration, since we're going to be finding these an infinite amount of these cylindrical shell strips, and we're going to be adding all of them, that is where this comes in. The final formula of the cylindrical shell, which is 2 pi, the integral of rx, which is this, so the function of r, which is the radius, by the way, r, and times height, the function of height. And this is essentially the final formula. And we'll be using that formula for solving this. Again, this is revolving around the y-axis. I did not put that. I should have put it. Y-axis. So you get that here. 2 pi integral of the function of radius times the function of the height. Now we will be substituting that. Again, as basis, we will be, and this helps me the most in solving this. We always draw a rectangle, this strip of rectangle that's parallel to the axis of revolution. So the axis of revolution is this y-axis. Now, the height, as seen before, the height is this. The height is this, the length of this thin strip. And you would notice that there's the height of this thin strip is just the function. And the function is x cubed. So we put x cubed here. Now, the radius, and note this because this helps me a lot too. The radius is always assumed to be the distance between this rectangular strip and the axis of revolution. So it's Actually, I'll change the color so that there's variation. Here, this is always the radius. If this is the height, this here is the height, which is the function. So I'll put hx. This is the radius. And you would notice that the distance between the rectangular strip and the axis of revolution is the value x. If we are solving for the value, if we are solving for the axis of revolution where the axis of revolution is x, the distance from the rectangular strip to that axis of revolution would now be y. But we'll be focusing on that more later. So here, I put on the guide here. That's why our radius becomes just x times the function of that height, which is x cubed. And we'll be solving from the integral then on. So x times x cubed is x raised to 4. Oh, by the way, the limits are 0 to 2. Since we're solving it in terms of x, we'll be starting from 0 to 2. So we get the integral of x raised to 4, which is just 1/5 x raised to the 5th power. We will be substituting the limits. So this becomes 0. The 0 when substituted to x just becomes 0, and 2 substituted to x becomes 2 raised to 5, which is 32 over 5 times 2 pi. And 32 times 2 pi is 64 pi over 5. We put a little box on it, and that's going to be our final answer. Now, I want to give this tip. If you don't know, particularly in cylindrical shells, if you don't know in what terms to solve with, sorry, let me rephrase that. If you don't know if you're going to solve in terms of x or in terms of y, what I would like to do is, again, draw this rectangular strip. And the rectangular strip is always parallel to the axis of revolution. And what I would find first is the radius. Because the radius, again, like I said, is the distance between the axis of revolution to that rectangular slip. And here, it's x, since this value between the revolution and that strip is x. And from then on, you would be able to know that, oh, you're supposed to be solving this in terms of x, since, of course, the radius is x. So yeah, I use that tip. I use that thinking a lot, and it might help you. Now for our final question. Let's say you are asked to find the volume of the bound of y is equal to square root of x, y is equal to x, y is equal to 0, and the x-axis. And again, this time it's revolved around the x-axis. Yeah. So I've graphed it, and it would look a little something like this. The graph. Again, you can see that for both the x and y axis, the limits are 0 to 1. Again, that 0 to 1 is not explicitly mentioned here in the given, but you could just get that by equating, again, both of the functions. So to start, we will be using the same formula, but now that we're doing it in terms of the x-axis, in terms of the revolution around the x-axis, we will be solving it in terms of y. So this time it's actually quite opposite. If in the disk and washer method you solve in terms of y when the revolution is y-axis, here it's opposite. If it's in terms of x-axis, if it's in terms of the x-axis, you would solve it for in terms of y. Sorry, that was a mouthful. I did not say that properly. Anyways, here, the formula stays the same, but we're just going to be altering it so that we will be solving it in terms of y. So we substitute our values, 0 to 1. Actually, I will be putting our guide the rectangle, this rectangle here. Again, to know if the rectangle is standing or to know if the rectangle is horizontal or vertical, always remember that it is parallel to the axis of revolution. So since it's parallel to the x-axis, the rectangle is horizontal. So we're going to be getting the height. The height again is this, the length of that strip, and the radius is the distance between that strip and the axis of revolution. So this time it's y, and it's because of this that we know that we are supposed to be solving in terms of y. So here, from 0 to 1, again 0 to 1, 0 to 1, we put that here as limits. We will be getting the integral of y, the ry, which is just y, as we established here, the radius, times y minus y squared. Now the reason this is y minus y squared, is we are finding again the height of this, the distance between, the length of this rectangle. So it is essentially this function, this linear function, minus this radical function, or sorry, square exponential function in terms of y. So to get that length, we will just be subtracting this function with this function. So essentially, the function that touches the top of the rectangle minus the function that touches the bottom of the rectangle. So we get y minus y squared. Sorry, this becomes y because x is just y, and this becomes y squared because we will be getting the square to remove the radical. So it becomes y squared. So in terms of y, square root of x becomes y squared. So that's here right now. And what we'll be doing is just solving this. So distribute y squared, y times y is equal to y squared minus y times y squared becomes y cubed. Oh, sorry, I think this is an error. Never mind the error. This is just y squared minus y cubed. So yeah, don't mind it. Then we're going to be finding the integral of each of this. So y squared integral is just y cubed over 3 minus the integral of y cubed, which is y fourth over 4. Hello, I'm back. Sorry, I had to alter this since I actually wrote the wrong things in the PowerPoint. So to to recall, we will this become y, if we distribute this, y times y becomes y squared, and y times y squared becomes y cubed. Okay, so we're going to find the integral of this. So the integral of y squared is y cubed over 3, and the integral of y cubed is y4 over 4, not 12. Sorry, I messed it up. So again, we will just be substituting the limits here in the y's. So this becomes instantly 0, and this becomes essentially just 1/3 subtracted by subtracted to 1/4, with 1/4. And if we get the LCM of this, it becomes 12. So 12 divided by 3 is 4, minus 12 divided by 4 is 3. So 4 minus 3 is equal to 1. Also it becomes 1/12. And 2 pi over 12 is just pi over 6. So this is essentially the volume of this bound that revolves around the x-axis. Okay, that will be all. I'm sorry for the error in the last number. Thank you for listening.